Let's keep moving forward. So let's talk about the Boltzmann distribution. I'm going to write that equation down right here. So the Boltzmann distribution goes as n sub I divided by n sub j equals, I'm going to write exp. And when I write exp, I am talking about natural number e, the inverse of the natural log, just so that we're not confused between fundamental charge e and natural constant e. So this is 2.71 something or other, right? And when I put these in brackets, that means this is all e raised to the power. So I'll do a little code here. If I say like exp2, what I'm referring to is e raised to the power 2, okay? So this is now the exponential of negative, and then this is the quantity e sub I minus e sub j, negative of all of this, all divided by k Boltzmann times T. Okay? And if you think about your unit analysis, k Boltzmann was joule per Kelvin. So a joule per Kelvin times a Kelvin is a joule, right? Let's never forget the dimensional analysis. So that's energy, so that's joules on top. K Boltzmann is a joule per Kelvin times a Kelvin. So this is just unitless, right? And for something to be in an exponential, it has to be unitless. Okay? So now what does all this say? Well, N is the population of molecules in state I. That can be the ground state, it can be the second state, it can be the 4 millionth state. It's just a general placeholder. So Ni is the number of molecules in state I that have energy sub I. Nj is the number of molecules in state J that have energy sub J. And so the ratio of these two states will give us the relative population of things. For example, let's say in the ground state compared to the next excited state. So this gives us a distribution or a population of what molecules have energy I or energy J or whatever we want. Okay? So let's consider a few postulates of the Boltzmann distribution. The higher the energy of a state, the lower its population. Okay, higher the energy of a state, so the higher up it is on the energy scale, the lower its population is going to be. The higher the temperature of a state, the lower its population. Okay? So similarly, if I take a system that has a high energy state populated, but I cool it down, molecules will come back down into the ground state. It will be less populated in the excited state as I cool something down. And more states are populated if those states are closer together, if there's a smaller energy gap. So let's take a look at a random fictitious set of states. We could think of these as perhaps maybe vibrational energy levels if you want. Okay, and if let's say we can cool these molecules down to exactly 0 Kelvin. If we can get them to exactly 0 Kelvin, then by definition, I'm just going to like highlight this thing, color it in. Every single molecule, every single one will be in the ground state. There will be not a single molecule found in a higher lying state, including the translations. Okay? So what if I heat something up to room temperature? Same molecule, same energy levels, but now I heat it up to room temperature. Well, I'm going to be giving this molecule thermal energy. I'm going to be giving it thermal energy so that it can populate higher states. All right, so perhaps now only a fraction of those molecules are in the ground state. Some might even be in the first excited state, and some might even be in that third excited state. So it's going to make a distribution of states given to us by Boltzmann. And even though this could never happen, if we could get something up to like infinite Kelvin, then technically we would be populating like all of these states with equal probability, which just won't happen, okay? But if I heat this up from like 298 Kelvin to let's say 1000 Kelvin, I will see more of these upper lying states becoming populated. This is true for the electronic levels, the vibrational levels, the rotational levels, and the translational levels. So now we can kind of start to get a glimpse when we talk about molecules moving faster as a result of them getting heated up, it's because we're promoting those upper lying translational energy levels and those upper lying rotational energy levels as well. Okay. And if we heat something to the point where it glows, like think about if you have an electric stove. You crank that sucker, it's glowing red hot. That's because you've gotten it so hot that now the electronic levels are becoming populated. And to release that energy, they're crashing back down and releasing light as a result. Okay? So let's keep going.